Hey everyone, welcome to my video on the solids of revolution using discs and washers. And what I want to do is just kind of walk through a lot of this worksheet and kind of get you used to the ideas of using a disc or a washer to calculate a volume of a region rotated around an axis. So the first thing we're going to do is just get the idea of what do we mean by a disc or a washer. So we're going to draw some rectangles perpendicular, so this part is important. We'll get to another method later where the rectangles are parallel, but for all of these we're going to be perpendicular. So I'm going to draw, say, a little rectangle here, and this rectangle is perpendicular to the line, and what we want to do is rotate it around this axis. So if I rotate that, then what I should get is what looks like basically just a solid flat. You might think of like a quarter or something solid, but usually we will call this a disc. So that's a disc right there. If I have a rectangle that is not perpendicular, or that is perpendicular but not attached to that line, so still perpendicular, running up and down, but not attached to this line, then I'm going to rotate that and see what sort of shape I get off of that. So now we get pretty similar shape, but there's this hole that's right there in the middle. So that hole that's in the middle makes this slightly different in our calculations, and this, they usually, you can think of it as like a squash donut or something like that, but usually this is what is known as a washer. And I think the name comes from just like the hardware where you're putting things together, those metal flat things with a hole in it. Those are known as washers, so that's a washer. So we got discs and washers. The important thing is discs are always attached to this axis of rotation. You're not ever going to separate, not going to get any holes. A washer may separate at some point, give you this hole as you rotate. So that's what we get, and what we call a disc and a washer. Question 2, what is the formula that I could use to find the volume of these rotated rectangles, these discs or these washers? And so we'll write those down in a second, but if you think about the face of this, right, I have sort of this radius r that's coming up here, and the face of that, the area, would just be pi r squared, and then we're multiplying by this little skinny thickness. So we got the area of that face times the thickness. So this would be a pi r squared, and then times whatever that thickness is. In this scenario, that might be a dx. If it were a different line, say vertical, then I might have a dy in that type of scenario. But this thickness, dx or dy, will depend on kind of which way those rectangles are going to go. Similar here, I'm going to have this large radius here for my outside circle, and then I'm going to take away this hole, which for that one I'll just say is this little r. So here we're going to get this pi times a big R squared for the area of this entire face right here, that huge circle. And then I'm going to subtract out the hole, so minus this pi times little r squared. And once I take that hole out, that's the area of this circular region right here, just going in here, and then we'll multiply times that thickness, which again would be, in this scenario, a dx, but if it were, say, rotated the other way, it could be a dy if that were a vertical line. So we either use a dx or dy depending on how the rectangles are rotated. If your thickness is just a little change in x, you're using dx. If it goes the other way, we'll use a dy. So these are the formulas that I'm going to use. So if I added all these up, so I'm just gonna put those down here. If I added all these rotated rectangles, what would I get for the volume of my object? So again, remember, adding up a lot of small stuff, that's what you get when you do an integral. So you're basically just going to do the integral of my pi r squared dx, again, or dy, usually running from some a to b, or if I happen to separate and get a whole at some point, I get this integral a to b of pi times big R squared minus pi times little r squared. And then again, either the dx or dy, depending on what my scenario might be. So these could change depending on which way it's rotated. So this is going to be my discs, the first one, and then the second one, that's going to be my washers. And that will be the setup for all the discs and washers that you're going to look at. Notice the only difference with the washers is that I have this hole where I don't need that subtraction because I don't have a hole if I'm using discs. All right, we'll go ahead and take a look at this one, and then I'll probably also show you a little bit what you can do with some CalcPlot 3D, maybe at the end of this video or in another video. So with this one, what we want to do is we have this region, and we want to just answer a few of these questions that are right here. All right, so the first question is going to be, what is the axis of rotation? And I'm looking at this object, trying to figure out how this kind of relates in there. And what I'm going to do is just go ahead and draw in. It looks like, say, from here, this point over here, we're getting sort of this parabolic arc coming over to here. So that's my edge of that parabola. And then the axis of rotation would be kind of right there through the middle. As this gets rotated around, then I would get that object. So I'm looking at my axis of rotation as sort of right there on the x-axis, that region right in there. We're also going to draw in a rectangle. So if I want to rotate something on here, let's go and draw a rough rectangle. I'm going to draw a rectangle in there. I'm actually going to redo that. All right, so here's the rectangle that I have, and that's the one that we want to rotate. So sketch one or two rectangles rotated. So we'll go ahead and rotate those. And then part C, find the volume of a general sample slice. So if I go ahead and rotate this, and then we'll think about what's the volume of that slice. So again, remember we are talking about this guy, pi r squared, and dx in this case, since I have a small change in x for that rectangle. So really all I need for that slice is to just find what is my r. So r in this case would be going from here up to here. So you could call that the y value, whatever the y is right at that point. But we want things in terms of dx. So I'm going to replace that y with this expression right here. So we're going to write it this way, pi y squared dx. And then I'm going to replace this y with the definition right here. So this negative x minus 3 squared plus 4. So that'll be part C. So the volume of a general sample size is going to be pi times this r, which happens to be negative x, what was it, minus 3 squared plus 4. That whole thing squared, and then my dx. And then set up an integral that represents the volume. Approximate the volume by evaluating to 2 decimal places. So we'll go ahead and just say, here's my integral of that pi times negative x minus 3 squared plus 4, all of that quantity squared dx. And the important thing here that we have left is the bounds. So where are these bounds going to go? So if we take a look at our figure again, looks like our x's are going to start here at 1, and then they're going to go all the way till we get over here at 5. So this would be 1 to 5. All of these rectangles are going to get rotated around. So this would be 1 to 5 for this integral. Now, just like all the other integrals, there's several ways you can try to do this. If you're going to do this by hand, you'd want to square this out, simplify it down to some power rules, take the integral, plug in your bounds, fundamental theorem. Like most of the rest of chapter 2, we're just going to use the calculator or Desmos to calculate this out. So let's go ahead and I'll pull that up real quick. Alright, so here is my graph. So there's the parabola we were talking about. And I'm going to do the integral from 1 to 5. And then, like some of the other things we've seen, I can either type this all in again, squared, since this is my r, or I could just put a pi times y1 squared, and then dx. And that will calculate it squaring this y that I've put up here. So this is usually my preferred method, just because you don't have to worry about like where parentheses are going to go and squaring other things that may be complicated and have more other parentheses in there and messing that up, especially on the TI-84. Using the variables command with the y1, y2 definitely helps. So that is just my personal recommendation for calculating these things out. So we get 107.23. So if I go ahead and put that in, we got 107.23. All right. Now, as far as some of the rest of this goes, we'll kind of finish this up in another video, but this time, right, on the second problem, we're going to be rotating around a different axis, and this one's going to be a little bit harder, a little bit trickier, so we'll go ahead and start that one in another video. Real quick before we finish this one out, I just wanted to show you in Calc.3D what you can do. So I've gone ahead and graphed our function here for the y top. Y bottom is just on the axis at 0. We're going from 1 to 5, so that shades in that part of the parabola. And then our axis of revolution, y equals 0, right there on the x-axis. And I can rotate that region if I want to see if that matches with what I expect. So that looks pretty similar to the object that we saw before. Again, if I want maybe not the edges, I can take those off, but it looks pretty much like what we had before. If I just want to show, say, a particular rectangle and rotate just that rectangle, I can do that here. Let's see, I am going to get a disk. It's right there. If I want to say slide this is what we're doing, right? We're adding all these disks over this whole entire region and seeing what that calculates out to. So as we add up all those disks with an integral, we'll get our value as our final answer. I think that'll do it. If you haven't seen the Calc.3D, do make sure you go back and watch that video if you want to know more about some of the features here.